Section 10.6 is titled torque. This is the rotational analogy for force. We know that, according to Newton's second law, if a mass is constant, that force equals mass times acceleration. Basically, force creates a change in motion or an acceleration. Torques cause an angular acceleration, a change in the rate of rotation. But torques are also related to an applied force. When we look at a rotational object, the torque placed on that object is due to some force a distance from the center or the axis of rotation perpendicular to that. So we're going to take a look at what torque really is, how to calculate it, and how to apply it in different types of situations. So torque is defined by the vector r cross f. Essentially, if we take this position vector r, we go from the axis of rotation to where the force is applied, and then we take the force vector and the cross product between the two, that will give us the torque. Now with cross products, we know that the resulting vector will always be perpendicular to the other two vectors. R and F basically define a plane here, which happens to be the same plane of this rotating disk. So this torque vector is going to be normal to that disk. That is going to give you your axis where we will change our rotation. The SI units for torque are newtons times meters. And although this is the same unit as the joule, torque is not energy. They're two very different ideas here. So again, torque is our rotational analogy to force. We don't want to use the cross product here. Instead, we want to use the magnitude. We can write the magnitude of the torque as RF times sine theta. Theta represents the angle between our position vector R and our force vector F. This allows us to ignore the directional properties of torque, but we can actually obtain them using the right-hand rule. Now, if I use the right-hand rule for cross product, I always take my right hand, and now I'm mirrored here, so it's going to look like I'm putting up my left hand. But I take my right hand and I move my fingers initially in the direction of the R vector here. I will then rotate them in the direction of the F vector. I rotate, and my thumb points in the direction of torque. So what this allows me to do is actually avoid using the more complicated vector equation, the cross product for torque, and simply calculate my magnitude and then determine the direction using the right-hand rule. Whatever's more convenient is oftentimes the technique that we choose. So using torque on different examples, and unfortunately, this force vector is going up to where the video window is, but here we look at the torque on a door. The doorknob is placed away from the axis of rotation. It's placed away from the hinge. Why do we do this? Well, if we look at this equation right here, torque is equal to RF sine 90 degrees. Notice my R vector goes this way. My force vector is 90 degrees with respect to that vector right there. And that makes sine 90 degrees 1. So essentially, the torque that I use to open the door to change its rotational motion is how much force I apply on the doorknob times the position of the doorknob with respect to this hinge. So this is why we don't put doorknobs very close to the hinge. If you have a doorknob right next to the hinge, that will make R small and place very little torque on the door. Makes no sense. We maximize the mechanical advantage here by moving the hinge as far away from, the doorknob as far away from the hinge as possible or within reason. And that maximizes our R. So for a given force, I don't have to apply a very large effort in order to open the door. But again, torque is R cross F in this particular case. R is the position vector. Again, how far is this force applied away from the axis of rotation? And of course, for the F is the applied force. Now, thinking about other situations where there's no torque, if I take my force vector, drive in the same direction as R, that is simply going to pull on the hinge. That's not going to create any rotational force here. It's not going to create any torque. The other problem I have essentially makes sine theta equal to 0. The other problem I would have is if I applied a force on the hinge, that's also not going to create any change in the rotational motion. There, that makes the R vector 0, and thus the torque will also be 0. So it doesn't matter that my force might be off at a little bit of an angle. I can apply a torque. The torque is going to be the product of the distance from the hinge, the amount of force that I apply, times sine theta, which is essentially taking a look and seeing how parallel F and R are. The more parallel they are, okay, the smaller my value for theta is going to be, and therefore the smaller the value for sine theta. If sine theta has its maximum value at 1, that means that this angle is perpendicular. So perpendicular forces create the largest torques. Here I have a wrench, and I'm going to take a look at the same problem again. I'm going to apply some force. I have some distance r from the axis of rotation to where the force is applied. And again, torque is R cross F. If I do my right-hand rule, my fingers will point originally in the direction of R. They will then rotate in the direction of F. So they point this way, then they rotate in the direction of F, R cross F. We go from R to F. And my thumb will point out of the page or out of the screen, and that indicates a positive torque. So for this crescent wrench right here, it's actually an adjustable wrench. It's Craftsman, it's not Crescent. There's a brand called Crescent. This will create a counterclockwise rotation. This positive torque will actually loosen this bolt. If I want to tighten the bolt, I need a negative torque or a torque in the clockwise direction. Okay, let's actually do a calculation here, but instead of using the cross product, I'm going to use the magnitude. Why do I do that? Well, for this particular problem, I've already said that I've used the right-hand rule. The wrench, the adjustable wrench, can only rotate in the X and Y plane. Here's the X axis. Here's the Y axis. So my torque has to be perpendicular to that. That's a positive or negative Z direction. I used the right-hand rule to tell me that it's the positive Z direction. And I can see here that, again, R times F, 0.4 times 100 newtons. I'm going to say that this wrench has a length of a little more than 40 centimeters, but the force is applied 40 centimeters from the axis of rotation. I put 100 newtons on this. I'm going to apply the force at 120-degree angle. Let's say I'm in a tight spot and I can't quite get that perfect 90 degrees, so I've got to do it at 120 degrees. I can see 0.4 times 100 gives me 40 Newton meters. The sine of 120 degrees is 0.866, and that's 35 Newton meters. Now, this is just a very simple adjustable wrench. It's adjustable so it can go on different types of bolts. But there are actually specialized wrenches called torque wrenches, which will tell you how much torque is being placed on a bolt. Let's say, for instance, I'm tightening something that's very sensitive. Maybe I'm putting a spark plug in. I want enough torque to tighten the spark plug such that no gases will escape from the cylinder of an internal combustion engine, but I don't want to over-tighten it so much that I'm going to damage the threads or over-tighten the copper seal. So in that particular case, I would use a torque wrench to get right the exact amount of torque that I want, and it would either have a mechanical indicator or a digital indicator. Some of these even beep to tell you when you have the exact correct torque. And they're very, very important for dealing with sensitive equipment. Another approach is to calculate what's known as the lever arm or moment arm and multiply that times the force. when we're drawing our force diagrams and we're trying to calculate the torque, sometimes we can determine what is known as a line of action for the force. And the smallest distance of that line of action to the axis of rotation is known as the moment arm or the lever arm. Okay, so D is a little bit different from R, but D, as you'll see, is actually R times sine theta. So we really don't change this equation that we have right here. We're really combining R and sine theta into one value called D. But again, on certain diagrams, I might be able to identify D better than I can identify R, and I can insert that into this equation, making the torque equation for magnitude very, very simple, just F times D. Another approach is to combine sine with F. Here I calculate the perpendicular force, and only the perpendicular force will contribute to the torque. So no different than from what we had before. It's still torque equals RF sine theta, but here I'm taking the perpendicular torque force, which is just my overall force times sine theta. I'm taking this orthogonal component in this particular direction right here, where the parallel component does not contribute to the torque. So we have to determine what is advantageous for the particular problem we're using. Which of these methods am I going to use to calculate torque? Am I going to just do straight out cross product, okay, where I know my R vector and my F vector in terms of its orthogonal components, I hat and J hat? Am I going to use this equation right here and then apply the right-hand rule to determine the direction of the torque? Just take the product of R, F, and sine theta. Is it easier to actually find the moment arm or lever arm than it is to find R? Is it easier to find the perpendicular components? Whatever is advantageous for that particular problem will determine, probably which method you'll use. Let's do cross product just to be certain that we know how to do this. We are going to say that the torque is equal to R cross F. I'm going to give this R vector some value, and I'm going to give this F vector some value. And I'm going to break it into its orthogonal components, where we have them in terms of I hat, J hat, and K hat, which indicate the X, Y, and Z unit vectors. Okay, so I'm going to place a force on there. This is my F right here. 50 newtons in the X direction, 20 newtons in the Y direction. So it's 50 newtons I hat, 20 newtons J hat, okay? And I have R here, where we have 0.3 meters. So R is moved off 0.3 meters in the X direction and negative 0.05 meters in the Y direction. So I'm going to take the cross product between this and this. It's very important that you get this in the correct order. I actually did an example of a cross product where I flipped these two, and I ended up with a torque that was pointing in the wrong direction. If you do these out of order, R cross F is actually the negative of F cross R. So I put this in my determinant, calculate the cross products using this 3x3, and I come up with these two components here. Now, if I look at this, I'm only going to have a K hat component because this Z component is actually the 2x2 determinant of this right here, okay? So we say 0.3 times 20 minus negative 0.0 times 50. The I hat and J hat components both have columns of zeros in them, so they're going to end up being 0. So it's actually an easy calculation to do because everything's in the Z direction. We knew this was going to happen because we're rotating in the XY plane, and torque had to be perpendicular to that. But 20 times 0.3 is going to give me it's going to give me actually I got this wrong, 6 Newton meters and then we subtract off of that 50 times 0.5, and that's going to give me 2.5. So I just have these out of order. I apologize for this. This goes here, but that's going to give me a net of 3.1 Newton meters in the k-hat direction. So I don't know why I put those backwards, but the net torque is in the positive k-hat direction. That means it's a positive z direction is coming out at you. And again, for this particular case, we are going in the counterclockwise direction. We are loosening up this bolt here. Okay. I didn't get this correct. This is 20 times 0.6. So 6 times 2.5, 6 times 2.5, that is going to give me 8.5. Wow. A little bit of a mess going on here. But in any case, torque on a pulley will have many different problems where we actually have to calculate the torque on a pulley. In this case, this pail is pulling down on this pulley. We did a similar problem earlier with this to determine angular acceleration. For connected bodies, we know that the torque is going to be equal to the mass of the bucket times acceleration. I'm sorry, the tension is going to be the mass of the bucket times acceleration of gravity minus the acceleration of the bucket. Okay, that equals 30 newtons. Please ignore that A there. And essentially, let's say the mass of the bucket's 5, the acceleration is 4. That's going to give me 30. So 30 newtons of tension here will be 30 newtons of tension here. I take the tension, multiply it by the radius of the pulley, and that will give me my torque. The tension is perpendicular to the position vector. So sine theta here for the pulley is almost always going to be 90 degrees, or sine of 90 degrees, which is 1. So torque is 0.5 meters. Let's say that this pulley is 1 meter across, or half a meter for radius. Multiply it by the tension, that's 30 newtons. That will provide a torque of 15 Newton meters, causing the pulley to rotate. Oftentimes we use gears, and I apologize, I have spiky gears here. The splines are usually not spiky like this. They use square teeth rather than these triangular teeth, but that's all I could draw here for this drawing. We know that the outer velocity of this gear is going to have to be equal to the outer velocity of this gear, okay? That means that they're going to rotate at different rates. We know that V is equal to R times omega. That's how we go from our transverse velocity to our angular velocity. So if the radii of these two gears are different, they are going to have different rates at which they rotate. And you see this before in gears rotating, that the smaller gear is going to have to rotate at a higher angular velocity to keep up with the surface of the larger gear. So we can use this to actually change the speed of rotation in a system, but we can also use this to change the torque. Gears are very, very important in changing the torque, because if this gear is rotating slower than this gear right here, okay, we will have different amounts of torque, which are based on the radius here. So again, the force on gear A is equal to the force on gear B. The force happens right at the spline right here where they come in contact with one another. We know that force is going to be related to torque. Torque is force times the moment arm. So I take the torque divided by the moment arm, set that equal to the force, and I see that the torque on gear A is going to be equal to the radius of A divided by B times the torque on B. So if I have so much torque on the smaller gear, I can increase the torque on this gear right here by simply having a different radius, okay? More torque also means it's going to rotate slower, so I can increase my torque, but my omega A is going to be slower there. So there is a relationship between these gears, how quickly they rotate, and their torque. Just like we have for most machines, the force times the distance here is going to be basically conserved for a machine, but here it's more like the torque divided by the radius is going to be the same on each. Now, when we deal with multiple torques, we simply do the same thing that we did with multiple forces. The net force on a body is equal to its mass times its acceleration. The net torque on a body is going to, by Newton's second law, be equal to the moment of inertia times the angular acceleration. So in dealing with some system, let's say that we're dealing with, for instance, a seesaw here, two children on a seesaw. What is the net torque on the system? I have to calculate the torque due to each child. Let's say that this child right here is some distance 4 meters from the fulcrum. This child right here is 2 meters from the fulcrum. I know it doesn't look like that in this diagram right here. But if I calculate the net torque, I can say, okay, well, this child creates a clockwise torque that's going to be negative. This child creates a counterclockwise torque that's going to be positive. So F1R1 plus negative F2R2, negative torque, is going to be equal to the net torque on the entire system. So I have 500 times 4 meters. This child's lighter, okay, but they apply more torque than this child who's heavier, closer to the fulcrum. And of course, as I do my calculation right here, I find that the net torque is going to be 2,000 minus 1,600, which gives me 400 Newton meters of net torque. This whole seesaw is going to end up rotating in the counterclockwise direction. This brings up the idea of levers. You've probably heard levers, tomato, tomato, that there are 3 different types of levers. There's a class 1 lever where the fulcrum is in between the 2 opposing forces, a class 2 where they're both on the same side, or a class 3 where they're both on the same side, but the effort and the load are flipped. Okay, so essentially our seesaw was our class 1 lever. We have a load on one side and another force on another side. And if they're balanced, then there's a net torque of 0. Okay. For the first class lever, the fulcrum's in between. For the second class lever, we're normally increasing the distance on the effort, what we're trying to apply this machine to apply some force. I should say we're trying our effort, what we're applying, we're trying to make our force smaller such that we can move a larger load. So this R on the load is smaller than this R on the effort, and that gives us a mechanical advantage. We can apply less force here, lifting more force here. And of course, we have the opposite case for the third class lever. Here, we're giving up mechanical advantage to move a load a further distance. Now, if we look at different systems, here we see a first class lever for a seesaw. Here we have 2 levers put together to create scissors. Okay, so this would be first class. Here's another first class. We have second class levers for wheelbarrows, for a wrench, for a nutcracker, and then third class levers for rowing. Okay. Yeah, that would be true there. Depending on how you put the force in a shovel, you can do this multiple ways. But most importantly, we see levers, in this case, a third class lever for the case of joints. Now, again, in lever systems, we use this idea of mechanical advantage to look at the ratio of the moment arms in the lever, where the moment arm of the applied force is oftentimes greater than the moment arm of the resistance to get some of this mechanical advantage. That's not always the case. But for the joints in our body, what we find is the muscles have a very small distance at which they can contract. So the muscles in a joint will actually give up mechanical advantage, will actually have a mechanical advantage less than one because of their small distance to create a larger range of motion. So for the elbow joint, for the knee joint, for the shoulder joint, the force is applied very close to the fulcrum or to the axis of rotation, and the resistance is further away, leading to a mechanical advantage that is less than one for the muscle. But again, that's for a greater range of motion. If the muscle were attached closer to the fulcrum of the joint, your amount of advantage would be greatly reduced. So for the bicep and tricep muscle, those are on the elbow. The bicep creates a class 3 lever, causing the arm to, I have to remember, to flex, the elbow joint to flex. The triceps create a class 1 lever. They're on the back side of the elbow, causing it to extend. For the knee joint, the quadriceps create extension. The hamstring creates flexion. And for the shoulder, the deltoid will cause the shoulder to extend, this joint right here, but then you have other muscle groups that cause it to close or to flex. You always have at least 2 muscle groups for each joint. Sometimes you have multiple muscle groups, but again, you have these muscle pairs. Muscles can only create force during contraction. Okay, they can only do work during contraction. So the bicep will rotate the angle such that the angle is less. The tricep will increase the angle. And again, you can see the direction of the force. You can see the position vector R here. And here's our load that we're lifting right here for the bicep. Now, what's important to understand is that the torque provided by muscles is not constant. The torque for muscles actually changes because during this rotation, this distance R is actually going to become slightly smaller depending on the angle. And what happens here is at 90 degrees, we actually get the greatest moment arm here, but the moment arm gets smaller at larger angles or smaller at smaller angles. Now, here's an idealized sketch of what the moment arm would do at different angles. This is actually not completely accurate because if we look at this, if we were to fully extend this, we'd still have some moment arm between our fulcrum and our muscle. But this overall trend shows us at small angles, our biceps have a lower torque than we do at 90 degrees, and then their torque becomes less again as we fully extend this. And this is why some exercise machines do a better job of changing the force. They'll actually use special shaped gears, which will reduce the torque at small angles and low angles, and will increase the torque when the mechanical advantage is greatest at 90 degrees. And this exercises the muscle more completely than if you simply just do a curl where the force is constant, the torque is constant, but the mechanical advantage or the moment arm for your bicep is constantly changing. So again, looking at torque, there are a number of different ways that we can calculate torque. This will become important for different problems where, again, we're going to apply Newton's second law, where the torque is going to be equal to the moment of inertia times the angular acceleration.